Okay, so we've now talked about all of our tests for series convergence and divergence. And now we're getting into the topic of what a power series is. This is really why we learned all of these tests for convergence for infinite series. Okay, so here's an introduction to this. We know, okay, find the sum of the series, 9 plus 3 plus 1 plus 1/3. Should recognize that as a geometric series with an R value of 1/3. Remember, the sum of a convergent geometric series is the first term over 1 minus r. So I'd get 9 over 1 minus a third, which is 27 halves. Another geometric series, 8 minus 4 plus 2 minus 1, r value of -1/2. And if I plug that into my sum formula, I'm going to get a sum of 16/3. So I just wanted to show you a couple examples and highlight that what we've now learned, I mean, at the beginning of all of this, it might have been somewhat surprising that you can add an infinite number of numbers and actually get a finite number, right? A lot of people would think if you add an infinite number of numbers, you get infinity. And we know that's true sometimes, but there are ways of getting an infinite series to equal a number. Now, another thing then, what if we work this backwards? Could I find an infinite series that adds to just a random number, let's just say 10? Well, if I manipulate this backwards and try to find, let's just stick with a geometric series, what I could do is just arbitrarily choose a first term. Let's just say I choose it to be 5. And if the sum's going to be 10, my first term's 5, I could algebraically solve for r to get 1/2. And now I know my series 5 plus 5 halves plus 5/4 multiplying by 1/2 would add to 10. Now you can probably imagine this wasn't the only infinite series that adds to 10. I could have picked a different first term, had a different r value, and I would find another series that adds to 10. So now think about where we are. We could pick any number and not only find an infinite series that adds to that number, we could find an infinite number of infinite series that add to any number. So this is very powerful. But now here's our goal. We want to find an infinite series that adds to a function in some cases. So if I started with this function, because it's going to be the easiest, 1 over 1 minus x, which is exactly the sum formula for a geometric series. It has the right form with a first term of 1 and an r value of x. My first term would be 1, and if my r value is x, I get 1 plus x squared plus x cubed, infinite series, and that would add to 1 over 1 minus x. Of course, it is an infinite series, and we've talked about converging and diverging. What would have to be true about my r value it would have to be between -1 and 1, right, to converge. Okay. And so we call this is a power series. This is a power series that represents this function. And using the geometric series idea, there's a lot of functions you could actually find a power series for. So here, if I had x over 1 minus x cubed, if it has that form of first term over 1 minus r, this time my first term would be x, my r value would be x cubed, I just keep multiplying by x cubed, and I can get an infinite series that equals that function. Once again, it would only converge if the absolute value of r is less than 1, which would be between -1 and 1. Okay, we call this by the way, is called the interval of convergence. Makes sense. Those are the x values I can use and have that converge. What about 1 over 1 plus x? I could always think of that as 1 minus negative x, 1 over 1 minus negative x, which means my r value would be negative x this time. So I would get the first term is 1 minus x plus x squared minus x cubed plus x to the 4th. And again, absolute value of negative x would have to be less than 1. So it would converge between -1 and 1. Now, there are ways of getting power series for other functions, and picking up from 1 over 1 plus x, if I integrated that function, we know the integral of 1 over 1 plus x gives us the natural log of 1 plus x. So what I can do is, if I know the series for 1 over 1 plus x is this, if I integrate both sides, integrate that polynomial, I get a new power series. I get x minus x squared over 2 plus x cubed over 3 minus x to the 4th over 4. And this could be expressed in sigma notation to capture every term. Okay, it's an alternating series. And this, by the way, there are going to be some functions whose power series representation are going to be more important than others. Like this is going to be one we're going to see again. We're going to work with this one. Now, as we saw, anytime you have an infinite series, that doesn't mean this series will converge all the time, right? What we want to find now is what values of x I can plug in for this series and have it converge. And this time, this series is clearly not geometric, right? I'm not multiplying by the same value to get from one term to the next. So to find the interval of convergence, we're going to need to use, okay, the ratio test. If you had put a number in for x, like 3 or 1/2 or something, and just looked at it like we've been looking at all of our other series, you would hopefully conclude the ratio test would be the best one to go with. We're going to check for absolute convergence as well, so we'll do the limit of the absolute value, a sub n plus 1 over a sub n. Raise everybody the n plus 1. We're really dividing by that or multiplying by the reciprocal. We're doing absolute convergence, so the negative ones don't really matter. We can just ignore that. I'm going to have x left over, and if I group the n over n plus 1, that goes to 1. So I get, what do I have left over is the absolute value of x, which is our, we were calling that quote unquote r value. Remember, by the ratio test, this series will converge only if the absolute value of r is less than 1. Remember that the ratio test is inconclusive if the absolute value of r equals 1. Okay, and there's an implication of that. We know then, if I set the absolute value of x less than 1, we know for sure it converges absolutely between -1 and 1. But if x was 1 or -1, the ratio test would be inconclusive. And so what that means is it could still converge possibly at either one of those endpoints. So we have to test them separately. And so what that looks like is, if you test, for example, x equals -1, you literally just put that into your series, -1. Here we have the same base, so I can add the exponents. And that looks a little strange, but if you wrote out the terms, you would see that when n is 1, 2, 3, every term is going to come out to be negative. And if I factor out the negative, this is just the negative of the harmonic series, right? The p series when p is equal to 1. Which we know diverges. So now I know that it diverges when x is -1. What about when x is 1? Well, if I plug in x equals 1, 1 to the n is just 1. And so that leaves me with the alternating harmonic series, which is one we've studied, which we know converges conditionally. Right? If we took the absolute value, it would diverge. So it converges on the condition that it's an alternating series. So now we can be a little more specific. This power series for ln of 1 plus x, which equals this in sigma notation, converges for x values between -1, not including, and including 1, right? And then just to give you an idea of what we can do with power series, and to show you how these work. So I could use this, like let's say I wanted to know what the ln of 3/2 was. Most of the time you'd want a calculator for that. But if I put in 1/2 for x, 1 plus 1/2 gives me ln of 3/2, and that means I would be putting in 1/2 in for my x's. If you really wanted the exact value, you'd have to do this for an infinite number of terms. But what we can do is approximate. If I just stopped here at my third power, my third degree power series, and simplify those fractions, you can do that without a calculator, you'll get 5/12. And just to see, 5/12 on a calculator is 0.4167. and the actual value of ln of 3 halves is about 0.405. So you can see they're pretty close. Now, if I wanted this approximation to be closer to the actual value, what I would do is use more terms on my power series. But then to show you why the interval of convergence is so important, if I tried to use my series to approximate the natural log of 5, where I have to plug in 4, if you do the first 3 terms and simplify it, you get 17 1/3. The actual value of ln of 5 is 1.6-ish. That's not even close. Now, the reason that wasn't close is because 4 is not in our interval of convergence, right? We chose a number to plug in that does not make the series converge. This is why knowing the interval of convergence is so important, because it tells you what x values you can replace to approximate some function. Okay, another big deal about this particular one. When we integrated the series for 1 over 1 plus x, which had a interval of convergence between -1 and 1, it would diverge at the endpoints because the r value has to be less than 1. And we got this series, and we just showed that it converges between -1 and 1, including the 1 in this case. But what we call the radius of convergence, the radius of convergence doesn't include the endpoints, okay? It's just, so in this case, the radius of convergence would be 1 unit, because from 0, you can go 1 unit in either way, either direction. And notice it didn't change, right? It still converges between -1 and 1, not including. Now, this one happens to also converge at 1, but definitely between -1 and 1. And so what happened when we started with this series and integrated, notice the radius of convergence, not including the endpoints, did not change. And this is true for all series. It's called the integration differentiation theorem. If you integrated or differentiate a series that you know converges between -r and r, again, not worrying about the endpoints, the new series was guaranteed to converge on the same interval. But you may have to test the endpoints, right, to see if it actually converges at the endpoints. Okay, so for example, let's do another one. 1 over 1 plus x squared, I can find that series, a power series for that function, by once again thinking about a geometric series with a first term of 1 and an r value of -x squared. And that would give me 1 minus x squared plus x to the 4th minus x to the 6th, and so forth. Because it's a geometric series, it's going to converge if your absolute value of r is less than 1, which, okay, that looks weird, but just think about it. What numbers could you plug in there and have it be between the absolute value be less than 1? Any number between -1 and 1. Now remember, for the geometric series, we know it can't converge at the endpoints. Your r value has to be less than 1, can't equal 1. Now let's try the same thing we did earlier. Let's integrate this, because if we take the integral of 1 over 1 plus x squared, that's another well-known function. That's the inverse tan function, the arctan. So if I integrate each of these term for term, I get a kind of a recognizable power series: x minus x cubed over 3 plus x to the 5th over 5 minus x to the 7th over 7. It's an alternating series made up of the odd powers, right? And then in sigma notation, you could express it this way. Now, we've got a new series that's not geometric, so we want to know, where does it converge for, right? What x values am I allowed to plug in? By that previous theorem, by the integration differentiation theorem, I'm already guaranteed that I know it's going to converge on the interval from -1 to 1 from our 1 over 1 plus x squared. But what that theorem doesn't tell us is what's happening at the endpoints. So we have to test those separately. What we're going to do next. Okay, so when x is -1, if you substitute that in for x, you can add these exponents. You get negative 1 to the 3n plus 1 times 1 over 2n plus 1. And you can show that this actually is an alternating series. If you plug in 0, 1, 2, you'll see that that's actually behaving the same way as an alternating series. And it satisfies all the requirements, so it does converge. Now, if we took the absolute value of that, we would get a divergent series. This 1 over 2n plus 1 would diverge because it's going to, by a limit comparison test, to 1 over n. So it converges conditionally at x equals negative 1. Now, if x is 1, you just get negative 1 to the n, 1 over 2n plus 1, which if you think about it, it's the same. So that would also converge conditionally. So now we know this series for inverse tan converges between negative 1 and 1, and it does converge at the endpoints, although it is conditionally. One kind of interesting thing about this particular series is that if you evaluate it at 1, which is right at the endpoint, so it does converge, you get this sequence of fractions, all of the odd numbers, the reciprocals of those alternating, and the inverse tan of 1 is pi over 4. So what that means is pi could be expressed as 4 times this infinite series, which is just kind of an interesting result, right? What in the world does pi have to do with the reciprocals of the odd integers, right? That's why pi is such an intriguing number. Okay, a couple more practice problems. The power series, so a lot of popular functions, we saw one for inverse tan, for ln, a lot of popular functions have power series. They can be represented with a power series. The power series for e to the x is 1 plus x squared over 2 factorial, x cubed over 3 factorial. We'll figure out later on how this power series is derived. Okay, right now that's not important. In sigma notation, it's just x to the n over n factorial. And what I want to know is, what's the interval of convergence? What would we be allowed to plug in for x and expect a convergent series? So what test would I use? It's got a factorial. Ratio test would be the best test. So you've seen this. We'll do a sub n plus 1 times the reciprocal. Remember, the n plus 1 factorial is really n plus 1 times n factorial, so the n factorials cancel. And I'll just have an x over n plus 1, which if n goes to infinity, that's going to be 0 for every value of x, right? If you give me any number and I divide it by infinity, I'm going to get 0. Now, by the ratio test, if you get 0, that means it's going to converge for all values of x. So this one converges from negative infinity to positive infinity. That's really powerful. That means if you want to approximate e to any power, you can choose any x value and plug it into this infinite series. If you use enough terms, it will be close to e to the x. Okay, one more, just for extra practice here. This is just a random power series. I don't know what function this would represent. It doesn't really matter. It's just practice finding the interval of convergence. Interval of convergence. And another one where you've got powers of n, I think the ratio test would be the best test to use here. You're going to use the ratio test quite a bit when you're doing intervals of convergence. And you simplify this all out, and you're left with the absolute value of x minus 3 over 2. That's your quote-unquote r value. To converge, we need that to be less than 1, which means x minus 3 over 2 has to be between negative 1 and 1. X minus 3 is between negative 2 and 2. Add the 3 over, x is between 1 and 5. Yeah, I've used this term, but let's be more precise here. Every power series has what we call a center of the series. If you plot these numbers where it converges on a number line, right smack in the middle, right at the center, is 3. And that's referred to as the center of the series. And it's not a coincidence that x equals 3 in your original series, if you put in 3, you would get 0. So you can actually spot the center of the series by just looking at that right there. Okay. Now, and then also to be a little more clear on the radius of convergence, the radius of convergence is how far away from the center in either direction you can go. So the radius of convergence in this case would be 2. Remember that the radius doesn't really care about what's actually happening at the endpoints, but we know the ratio test would have been inconclusive at the endpoints, so we have to check them separately. If you plug in x equals 1, you're going to be left with negative 2 to the n over n to the 4th divided by 2n plus 1. If you separate negative 2 to the n as negative 1 to the n times 2 to the n, and then split up 2 to the n plus 1 as 2 to the n times 2, those will cancel. And we end up with an alternating p series where p is equal to 4, clearly converges, and not only that, it converges absolutely, right? If it wasn't even alternating, that would definitely converge. If x equals 5, you're going to get 2 to the n over 2 to the n plus 1, simplifies to not an alternating series, but a series that converges absolutely, right? So in this case, our series converges between 1 and 5, including the endpoints. All right, that's it for this one.